3.4 Conserved quantities in simple systems. The Hamiltonian for a simple system of particles is described next, typically one element or small group of elements, two linked somehow, but only in context of identifying integrals of the motion, such as conservation of energy, momentum, and angular momentum. Further discussion of Hamiltonians is then done in Chapter 6. Consider a generalized coordinate system Q sub I, where I is the component in a system with s degrees of freedom. The particle's cumulative dimensions of free motion are all counted towards s. Likewise for the associated velocities. Q sub I. There are thus s degrees of freedom for the generalized coordinate and s degrees of freedom for the generalized velocity. This gives rise to 2's initial conditions to specify the motion. In a closed mechanical system, this would appear to indicate 2's conditions and associated constants or integrals of motion, but the appearance of time in the velocity as a differential means t and t plus t sub 0 have the same equation of motion, so one of these 2's constants is merely t sub 0, a choice of time origin. Let's consider symmetries of the space of motion and implications given the Lagrangian formulation.
See the next equation. First, consider homogeneity in time, which means closed system or open system but with time-independent external field. Either way, have the fraction with numerator partial differential L and denominator partial differential T equals 0, and with reuse of the Euler-Lagrange relations.
See the equation shown. Thus,
Equation 3-11. The conserved quantity with time is energy, denoted by E. Note that additivity of energy on subsystems then follows from additivity for the Lagrangian, and the explicit additivity indicated by the sum. If L equals T of Q dot Q minus U of Q and T of Q dot Q proportional to dot Q squared, which is typical, then the standard energy conservation in the form of kinetic energy plus potential energy results.
Equation 3-12. Next, consider homogeneity in space, and start from a variational expression on the Lagrangian assumed not explicitly time-dependent, where an infinitesimal displacement should not alter the evaluation of the Lagrangian when delta q sub I is not equal to 0.
See the next equation. Net forces and moments on a closed system sum to 0. Specialized use of this will be shown in Sector 5.1. If we substitute back the Euler-Lagrange relation to get an explicit total time derivative term.
See the equation shown. From the total time derivative relation we get a constant of the motion corresponding to conservation of momentum.
Equation 3-13. Where for systems with T of Q dot Q proportional to dot Q squared for each of the particles, this simplifies to the standard form. Note, with two particles we have f vector sub 1 plus f vector sub 2 equals 0, which is equivalent to saying action equals reaction, i.e. Newton's third law is a special case of conservation of momentum and Lagrange's equation.
To go with our generalized coordinates and velocities, the generalized momenta and forces are, see the next equation, equation 3-15, where Lagrange's equations are simply
equation 3-16. Now let's see what happens due to isotropy of space. For this we shift from generalized coordinates to a three-dimensional radial position vector with infinitesimal rotational displacement given by. The variation in the Lagrangian should be 0, now indexing over individual particles.
See the equation shown. Substituting the EL equation and definition of generalized momentum.
See the next equation. Thus arrive at
equation 3-17. The quantity m vector is the angular momentum, and it is conserved. There are no other additive integrals of the motion, e.g., no other global spatial symmetries than homogeneity and isotropy of space. Now that we know angular momentum is conserved, we can begin to explore the ramifications of this. Angular momentum in 1D is trivially 0, thus we must move to problems with 2D unconstrained motion or 3D motion. Let's start with the spherical pendulum.
Example 3.12. The spherical pendulum. Consider figure 3.4, but with tension support and with motion of mass allowed in 3D, e.g., no longer horizontally planar. The Cartesian coordinate of the mass is. See the equation shown. Their time derivatives are straightforward. See the next equation. The Lagrangian is thus.
See the equation shown. For the equations of motion, we start by elimination of the conserved angular momentum about the z-axis.
See the next equation. Eliminating the θ dependence in the Lagrangian by use of its conserved quantity, we then get the revised Lagrangian.
See the equation shown. Where now, thus, exercise 3.12. What is the natural frequency in the small angle approximation?
Example 3.13. Table with a hole, threaded by a line with masses at the ends. Let's consider another scenario where the angular momentum about a particular axis is conserved. Consider a table with a hole. A tension line threads the hole. The end of the line hanging under the table has mass m sub 2 attached. The line has negligible mass, while the end resting on the tabletop has mass m. The initial force balance equations provide. See the next equation. While the force, in terms of the potential function, provide.
See the equation shown. Thus the Lagrangian is.
See the next equation, which can be rewritten.
See the equation shown. We can drop constant terms from the Lagrangian, since they make no change in the EL equations, thus no change in the equations of motion. So dropping the constant term and regrouping.
See the next equation. We can now proceed with the evaluation of the Lagrangian, again starting with the conservation of angular momentum term. Thus we have.
See the equation shown. The remaining equation of motion is. For small we then have.
Thus we can write. See the next equation. The latter result for the R equation of motion is indicative of a repulsive potential, which then begs the question, when do we have stable orbits?
See the equation shown. Thus, exercise 3.13. Could this apparatus be used to weigh unknown mass m sub 2? Describe a process to do this. Example 3.14. Revisit the single pendulum with horizontally oscillating support. Let's now revisit the single pendulum when the point of support is oscillating horizontally. The pendulum moves in the plane of the paper. The string of length L does not bend. The point of support P moves back and forth along a horizontal direction according to the equation x equals ACOS times omega t, and omega is not equal to the square root of times g of slash L. 1. Let's start by writing the Lagrangian for this system and obtain Lagrange's equations of motion. Don't forget the generalized force when writing Lagrange's equation for x. Have, thus. Also have the usual to then write the Lagrangian. 2. Next, solve the above equations of motion at first order in small oscillations, and find the steady-state solution for, in terms of m, a, and. We are not interested in the solution oscillating at the natural frequency of the pendulum. Thus, so have where the RHS is an effective force slash m. And we have the solution.
Exercise 3.14. Repeat but with a vertically oscillating support.